Dear students, in this session we are going to discuss relations and functions, chapter 1st of the NCERT class 12 maths book. Actually, this is the continuation of the chapter relations and functions we learned last year. So let's recollect some points we learned last year, like subsets, Audit pairs, Cartesian or cross product, then relations and functions. Its continuation we are going to learn in this chapter. So what is an Audit pair? 1, 2, A, B. These all are Audit pairs. A pair of numbers or elements grouped together in a definite order, that is called Audit pairs. So 1, 2 is an Audit pair. AB is an Audit pair. Let's recollect what is subset. Let A equal to 1, 2, 3, 4 and B equal to set 2, 3. We say that B is the subset of A because all the elements of B are there in A. B is the subset of A. What is Cartesian product or cross product? If A equal to set 1, 2, 3, 1, 2, 3 and B equal to set 4, 5, A cross B is equal to 1, 4 Audit pair, 1, 4, then 1, 5, then 2, 4, 2, 4, then 2, 5, 3, 4, 3, 5. This is A cross B. How about B cross A? B cross A is equal to 4, 1, then 4, 2, then 4, 3, 5, 1, 5, 2, 5, 3. This is A cross B and this is B cross A. How we define this? If A and B are two non-empty sets, then the cross product of A and B is the set of all Audit pairs of elements from A to B. Similarly, what about B cross A? B cross A is the set of all Audit pairs of elements from B to A. If n of A, the number of elements, n of A is equal to, here n of A equal to 3, here n of B equal to 2, then n of A cross B is equal to n of A into n of B. 3 into 2 is 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. N of A equal, if n of A equal to m and n of B equal to n, then n of A cross B equal to m into n, mn. Now, what exactly is a relation? Consider two non-empty sets A and B. Then a relation R from A to B is the subset of the cross product of A and B, subset of A cross B. A relation R is the subset of A cross B. But this subset is derived by describing a relationship between the first element and the second element of the Audit pair. Suppose this is a relation R equal to set 1, 1 and set 2, 4. This is the first element or X element and this is the Y element. So this is first, this is second, this is first, second. How they are related? The second element is the square of first, that is Y equal to X square. Check. Square of 1 is 1, square of 2 is 4. So there is a relation between the first and the second element. if n of A equal to P, n of B equal to Q, number of elements of set A equal to P and number of elements of set B equal to Q, then we know that n of A cross B will be PQ. Number of elements of A cross B will be PQ. If the number of elements of A cross B is PQ, then the number of subsets of A cross B will be 2 raised to PQ, which is equal to the number of relations from A to B. Since the relation is a subset of A cross B, so number of relations from A to B is equal to 2 raised to PQ. We will learn different types of relation. The first is empty relation. If a relation has no elements, then it is an empty relation. If a relation has all the elements of the given set, then it is universal relation. So empty relation and universal relation. Now let me explain this with an example. Let A be the set of all students of a boys' school. There is a relation defined on this set A is R equal to set the ordered pair AB such that A is sister of B. The relation is A is sister of B. Since it is given that it is a boys' school, so there will not be any sister, there will not be any girls. So it is an empty relation. And there is another relation R dash equal to set AB such that difference between heights of A and B is less than 3 meters. It is always correct that difference between heights of two students will always be less than 3 meters. It will not be 3 meter or greater than 3 meters. It will always be less than 3 meters. So here in this case, the relation is the complete set itself. So this is a universal relation and this is an empty relation. We have learned now empty relation and universal relation. Now we will learn reflexive relation. Reflexive relation is for every A belongs to the given set A, capital A, the ordered pair A and itself A belongs to the relation R. I'll explain with an example. Let set A is equal to 1, 2, 3, set 1, 2, 3, and there is a relation defined R equal to set 1, 1, 1, 2, 2, 2, 2, 3 and 3, 3. If we take the first element from set A and we check with the relation given according to this definition, reflexive relation, if we take 1, 1, 1 should be there. It is there, 1, 1 is there. What else? If we take 2, 2, 2 also there. And if we take 3, the third element, 3, 3 also there. So for every element belongs to the given set A comma A belongs to R. This is reflexive relation. Let's learn symmetric relation now. Symmetric relation is for every A comma B belongs to the given set A comma B belongs to R implies B comma A belongs to R. If AB is there in the relation, then A also will be there in the relation. Let's see with an example. There is a set A equal to 1, 2, 3 and we define a relation from this set R equal to 1, 2 and 2, 1. So according to this definition, if we take this pair 1, 2 is there, then 2, 1 also is there. So this relation is a symmetric relation. 1, 2 relation R is equal to set 1 to 2, 1. So it is a symmetric relation. Next is transitive relation. Its definition is for every A comma B comma C belongs to the given set A if AB belongs to R, AB, the audit pair AB belongs to the relation R, and BC belongs to the relation R, which implies AC belongs to R. AB belongs to R, comma BC belongs to R implies AC belongs to R for every A, comma B, comma C belongs to the given set A. If a relation is reflexive, symmetric and transitive, then we call that relation as equivalent relation. We will do a problem, we will do an example satisfying all these three relations, and we will prove that it is an equivalence relation. Now, a relation R in the set Z of all integers is defined as R equal to set xy such that x minus y is an integer. This is the relation, x minus y is an integer. We will check whether the first is whether this is reflexive or not. So, for every x belongs to Z, for every element, for every x belongs to Z, we know that x minus x itself, x minus x is 0, which is an integer. So, x comma x belongs to R. If x comma x belongs to R, this ordered pair belongs to R, then the relation is reflexive. Clear? Now, let us go to, we will check whether it is symmetric or not. For every x comma y belongs to the set of integers Z, if xy belongs to R, then we can say according to the definition x minus y is an integer. If x is an integer and y is an integer, then x minus y is an integer, which implies that y minus x, which implies if x minus y is an integer, then obviously y minus x will be an integer. That means y x belongs to R. So, if xy belongs to R, then yx belongs to R, then this relation R is symmetric. Now, we have to prove this relation is transitive or not. Let xy belongs to R, x comma y belongs to R and y comma z belongs to R, the given relation. For all x, y, z belongs to the set of integers Z. Now, this implies that according to the definition here, x minus y is an integer. That means if xy belongs to R, x minus y is an integer. If yz belongs to R, y minus z is an integer. So, x minus y and y minus z are integers according to the question. That means if we add this, x minus y plus y minus z is also an integer, Cut this minus y and plus y, we get x minus z is an integer, x minus z is an integer. That means x comma z belongs to R. So, what is the condition? xy belongs to R and yz belongs to R, then we got now xz belongs to R. Therefore, this relation is transitive. Now, we prove that the given relation is reflexive, symmetric and transitive. Therefore, this relation is an equivalent relation. It is time to wind up this class now. Hope you have understood this clearly, and further portion will be discussed in the next class. So, stay tuned for a new update.